In this session, we discuss link budget and fade margin, which are the tools useful to predict radio hop outage probability. Up to now, we have discussed free space propagation. Now, we consider what happens in terrestrial radio links, that is, when a radio link is installed close to the Earth's surface and electromagnetic waves propagate through the atmosphere. You must take account of a number of phenomena caused by the presence of the atmosphere and the ground, which may severely affect electromagnetic propagation. Generally speaking, propagation anomalies in terrestrial radio links are in some measure dependent on transmitted frequency, hop length, climatic and weather conditions, terrain profile along the radio link path, and finally, electrical parameters of ground. Let's now look more specifically which are the propagation anomalies caused by the atmosphere and the ground. First, the atmosphere is not a homogeneous medium. This produces wave refraction. As a result, the wavefront does not propagate along a straight line, but it is curved in some measure. Moreover, the atmosphere is made of molecules like oxygen, and in particular events, particles like raindrops or even hail and sand may be present. They produce absorption and scattering effects. Finally, terrain roughness may represent an obstacle to wave propagation. Again, this is related to the propagation direction, which is not a straight line. Terrain profile and bending in wavefront direction are the key factors in assessing visibility from the transmitter to the receiver. While, in our visual experience, we are used to the conditions of optical visibility, we stress the point that conditions for radio visibility are not the same, as we will see in future sessions. On the other hand, propagation over flat terrain may be affected by wave reflections. This is even more frequent for radio links over a body of water. You can take note of the list of propagation anomalies we've just seen as an index of what we're going to discuss in the future sessions of this course. For the moment, let's just consider the effects of propagation anomalies in general terms. Propagation anomalies in terrestrial radio links have an impact on the received signal. The received signal level may be lower compared with free space conditions. In most cases, we have a flat attenuation. That is, all the spectral components of the signal at different frequencies suffer the same attenuation level. However, in some cases, the received signal may even be distorted. In the case of signal distortion, you can observe that the shape of the signal spectrum is modified. This means that the spectral components at different frequencies suffer different attenuation levels. Coming to the duration of anomalous propagation events, short-term events can be observed, like a lower level of the received signal caused by rain attenuation or multipath phenomena. Speaking of short-term events, we generally use the term signal fading instead of attenuation. On the other hand, we can observe long-term or even permanent anomalies, like, for example, attenuation caused by terrain obstacles. The link budget is the tool that enables us to make a list of all the gains and losses undergone by the signal from the transmitter to the receiver. This includes the role of radio equipment, as well as propagation impairments. Starting from free space conditions, we first consider permanent impairments like diffraction from obstacles and atmospheric absorption. Taking account of such losses, we get an estimate of the signal power which is expected to be received for most of the time. This is what we call received power in normal conditions, or nominal received power. Note that very often, permanent propagation losses are rather small or even negligible. As a result, nominal received power may be rather close to what is computed for free space propagation. Here you see a scheme where the main items in a link budget are listed. Please note that logarithmic units are used. Power levels are expressed in dBm, while gains and losses are expressed in dB. Now it is clear why we use the term budget. Gain and losses are added with a positive or negative sign, increasing or decreasing to power level of the transmitted signal, just like in a financial budget. Note that, at this stage, only long-term propagation impairments are listed in the link budget. The link budget gives us the information useful to get an estimate of the radio link reliability. We can ask the question, is the received power sufficient to guarantee a reliable connection? To answer this question, we compare the nominal received power, P sub R, with the receiver threshold, P sub TH. Receiver threshold is the minimum received power required to guarantee a given quality of the detected signal. Receiver threshold is typical of a given radio receiver, and it is part of data provided by equipment manufacturer. The fade margin is computed as the difference between nominal received power and receiver threshold. This margin is useful to cope with additional attenuation caused by short-term impairments, mainly rain or multipath fading. In many fields of engineering, it is necessary to take some margins in the design. Think of a bridge designed to carry a lot more weight than the average expected. In point-to-point radio link design, typical fade margins are rather large, up to some 30 or 40 dB, or even higher. This means that we are sure that a satisfactory quality of the detected signal at the receiver is guaranteed as long as short-term fade depth is not larger than fade margin. And with a large fade margin, then the receiver is capable of operating correctly, even with rather deep fading. This figure summarizes what we expect when the received signal power is at a given level. Starting at the top of the figure, we move from free space propagation to moderate attenuation and finally to deep fading. Below the threshold, an outage condition is observed. Note that impairments like interference or signal reflection do not reduce the receiver signal level. Rather, the effect is to degrade the detection process at the receiver. A degradation of the receiver threshold means that we need a slightly higher signal level at the receiver to compensate for impairments like interference and to guarantee the desired detection quality. Finally, we arrive at the estimate of outage time. That is, the time when the signal quality at the receiver is below a given quality. The outage time during some observation time, T sub O, is computed as the product of T sub O times the probability that the received signal power is below the receiver threshold. Remember the fade margin definition. The same probability can also be computed as the probability of fade depth, F sub D, greater than fade margin Fm. This is valid if we assume that the transmitted signal does not suffer any distortion due to propagation. On the other hand, if some distortion in the received signal is expected, then the outage prediction formula has to be completed with an additional term. So, we read it as outage probability caused by signal distortion, given that the received signal power is above the receiver threshold. Please note that in the formula, the slash sign means given that, or, if you prefer, under the assumption that. A final comment. These formulas are useful to clarify the concept of outage time prediction, as it is related to the received power level and to additional impairments in the received signal. The formulas we have just discussed do not provide practical means to predict outage time. To do so, we need statistical models of propagation impairments, like rain attenuation or multipath fading. This will be the topic of the next sessions.